Welcome back to Advanced Skills Learning. Today we're doing a full RAG architecture deep dive, from ingestion all the way to final answers. This video is important because most RAG systems don't fail randomly. They fail systematically, and almost always before the LLM ever sees a prompt. When teams say, "Our RAG doesn't work," what they usually mean is that the system is returning weak or inconsistent context. And once bad context reaches the model, even the best LLM can only guess. That's why RAG must be treated as an architecture, not a feature. RAG is not just an LLM connected to a vector database. It's a multi-stage system with clear boundaries, responsibilities, and trade-offs. Each stage feeds the next, and small design decisions early in the pipeline compound into large quality differences at the end. At a high level, RAG consists of two pipelines. The first is the offline ingestion pipeline, where knowledge is prepared and indexed. The second is the online query pipeline, where user questions are answered in real time. These pipelines evolve independently and often break independently, which is why debugging RAG can feel confusing without a system-level view. Ingestion begins with source data. This may include PDFs, internal documentation, support tickets, wikis, or database exports. These sources vary widely in structure, quality, and update frequency. If freshness and coverage are not designed into ingestion, the system will confidently answer questions using outdated or incomplete information. Before chunking, most systems perform preprocessing. This includes cleaning text, removing boilerplate, normalizing formats, and extracting structure such as headings, tables, or sections. Skipping this step often leads to embeddings that capture noise instead of meaning, which quietly degrades retrieval quality. Chunking is one of the most critical and underestimated decisions in RAG. Large chunks tend to mix unrelated ideas, while very small chunks lose the context needed for reasoning. Overlap, structure-aware splitting, and semantic boundaries all matter. Poor chunking doesn't just reduce accuracy, it makes failures unpredictable and hard to debug. Once chunks are created, they are converted into embeddings. Embeddings represent semantic meaning as vectors, allowing similarity search instead of keyword matching. Different embedding models emphasize different aspects of meaning, so changing the model can completely change retrieval behavior even if the data stays the same. Quick check, 2 seconds. What is the biggest risk of overly large chunks? A. Slower embedding generation. B. Irrelevant retrieval. C. Higher storage cost. D. Lower cosine similarity. Keep your guess. The answer is B. Irrelevant retrieval. Large chunks blur intent and pull in unnecessary context. Embeddings are stored in a vector database along with metadata such as source, timestamps, document type, or access permissions. The database is not just storage. Indexing strategy, distance metrics, filtering, and metadata constraints all affect both latency and relevance during retrieval. When a user submits a question, the online pipeline begins. The question is embedded using the same or a compatible embedding model, ensuring that similarity comparisons are meaningful. At this stage, query routing, metadata filters, or hybrid search logic may narrow the search space before similarity search even runs. Retrieval produces a set of candidate chunks, but retrieval alone is rarely enough. These results are ranked and selected, typically using top K logic. However, increasing K often reduces quality by introducing noise. Re-ranking models help reorder results based on deeper semantic relevance rather than raw vector distance. Quick check, 2 seconds. What usually improves answer quality the most? A. Increasing top K. B. A larger LLM. C. Better retrieval precision. D. Longer prompts. Keep your guess. The answer is C. Better retrieval precision. High-quality context beats more context every time. The selected chunks are assembled into a structured prompt. This step determines how the LLM interprets the retrieved information. Prompt layout, ordering, instructions, and formatting all influence how the model reasons over context. Context windows are hard limits, forcing explicit trade-offs in what is included and what is dropped. Finally, the LLM generates an answer grounded in the retrieved content. Even with good retrieval, the model remains probabilistic. It may overgeneralize, miss nuances, or hallucinate connections. This is why guardrails, citations, validation, and monitoring are architectural necessities, not optional add-ons. The key takeaways are these. First, RAG is a system, not a trick. Reliability comes from how ingestion, chunking, embeddings, retrieval, ranking, and prompting work together. Second, retrieval quality matters more than model size. A smaller model with precise context often outperforms a larger model with noisy inputs. Third, observability is essential. If you cannot trace where relevance is lost, you cannot systematically improve the system. Thanks for watching. If this video helped, like the video and subscribe to Advanced Skills Learning for more Gen AI explainers, practical architectures, and quick quizzes to test your understanding.